Now that we've learned how to derive the equations to get shear and moment diagrams, we can talk a little bit about some shortcuts and some relationships in these shear and moment diagrams that'll make it a lot easier and a lot quicker for us to be drawing these diagrams. So one that we kind of touched on in the last video is that these have calculus relationships, right? That our load equation, right, our load W, is dv dx, right? Derivative of shear gives us our load equation. And shear is dm dx. The derivative of our moment equation gives us our shear equation, right? And we can write these the other way as integrals, right? That our shear is the integral of our load equation, right? The area under the curve of our load equation is how we get our shear, or that our moment is the integral of our shear equation. So we can use these relationships as shortcuts to find our equations. We can also use these graphically, right? Just as we're making these graphs, we can use the rules that we've learned of calculus, seeing that the slope of one becomes the value of the other graph, area under the curve becomes another value in the other graph. All of these relationships that we learned graphically in calculus are going to apply to these shear and moment diagrams. So a couple more relationships we'll touch on before we see how we kind of apply these in a shortcut manner is some basic rules of how we can look at applied forces and moments and recognize them in the diagram. So one is that whenever you have a concentrated force on your beam, let's say 10 kips or something here, a concentrated force will only affect the shear diagram. Concentrated force only affects shear diagram, but not the moment diagram. Only affects the shear diagram. It's not going to have any effect on the moment diagram, whereas a concentrated moment, which would be just an applied moment, you know, somewhere on this beam, maybe 5 kip feet, something like that. A concentrated moment will not affect the shear diagram and will only affect your moment diagram. Another thing to note is an internal hinge, right? So when we were looking at compound beams, say this was a compound beam that had a pin in the middle of it connecting two separate beams, beam AB and beam BC. An internal hinge there, an internal pin. If there's an internal pin in the compound beam, anywhere there's an internal pin or hinge, moment equals 0. Which is very helpful when you're checking yourself and very helpful when if you're ever working with a compound beam. The moment has to be 0 at the point of that internal. One more thing I'll note is that our positive convention on these things, right, as we've been drawing them, where we make a cut in our beam, our V is down, our shear is down, and our moment is counterclockwise. And we'll notice that anytime we have a downward shear or a counterclockwise moment, we consider those in the positive direction, right? But on our shear and moment diagrams, both of those things shift the graph down. So in this example, this 10 kip applied force here would cause a downshift in my shear diagram. Say I was at 0, and it would shift down by 10 on my shear diagram, and only on my shear diagram, wouldn't affect my moment diagram. Just that concentrated force there. Whereas this 5 kip counterclockwise, again, if I were, traveling along, then I would go down by 5 right, where that moment is applied. Right, so each of those, this convention here, this is what we use. This convention shifts the graph downward. If it's opposite, if V is pointing up, if M is going clockwise, then it's going to shift the graph up instead of down. So let's take a look at some examples of how we might apply these shortcuts. So for these examples, in the interest of saving time, I'm going to go ahead and just give you the reactions, but of course your first steps always be solving the reactions, drawing your free body diagram and solving for those reactions. But here we're going to go ahead and start with that already given to us so we can just focus on the shear and moment diagram. So in this one we have this cantilevered beam. It is fixed on a wall at A with a free hanging end on the left side. And it's got this 2 kilonewton applied force on the left end with 1.5 kilonewton per meter load from the center of the beam to the right side. So if I were to just look at this and think about some of those things that we've just discussed, the calculus of it all and how applied loads affect it. What I'm going to do is, one, I'm going to divide it into regions of load continuity first. So my first one is that I know from 2K until we hit that distributed load, at 2 kilonewtons till we hit the distributed load, is going to be a continuous load. And you may think, well, there's no load there at all, right? There's only the 2 kilonewtons and then there's nothing on the load. But that's still technically a load, right? It's just that the load equation here would be 0, right? And so when we integrate, that's why we get a constant for our shear. So that constant here, this is our shear diagram, put right here, and our moment diagram we'll put down here. This is in kilonewtons and kilonewton meters. So I've got my shear. One, it's an applied concentrated force and it's going downwards, so I know it's going to push that graph downwards by 2. Right? Immediately, -2. The loading is constant, the loading is 0, so it's going to keep its straight line across. Right? We went from a 0, we integrated, we got a constant. That constant is -2. This is all just by inspection. Right? We're avoiding writing out all of these equations and going through the math because of our background knowledge in calculus, we can just assume these things, right? We know how integrations work, we know how derivatives work, we understand area under the curve and the slope becoming, influencing your other graphs. Because we know those things, we can say, all right, it's just -2. Integrated my load here, I have just -2. Now, my distributed load is where things get kind of interesting, right? Because now, instead of having a load of 0 here, I have a load of -1.5. And that load becomes the slope to my shear equation, right? If I integrate that load, then I get -1.5 times x. And plus some constant, which, happens to move it to the -2 marker. So if I draw this, I'm drawing a line of slope with a slope of -1.5. And since I know that I'm going from this -2, it's connected here. There's no applied load, it's just distributed load. So it goes from that -2 spot down that 1.5 slope over the 2 meters. So I have that 1.5 times 2 gives me -3. So -2 plus -3 is going to give me -5. But I didn't actually have to do that calculation to get that -5 because I know that my shear and moment diagrams should always start and end at 0. So the thing that brings this back up to 0 is my AY reaction right here of 5 kilonewtons. Going upwards, it's pushing my graph back up from the -5 to 0. So even if I didn't bother to calculate, I could know that just from being able to get back to my center line, getting back to 0. Right? It's like imagining that you're just the most minuscule part to the left or to the right where that clicks over from the reaction, right? So it's like it's 0 and then immediately clicks over to that -2. -2, and then it goes to the -5, and then immediately clicks over to the 0 right after that reaction force happens at the very end of the beam. So that was so much quicker than having to derive the equation for those shears. And we can take what we know about calculus and use the shear diagram to now generate a moment diagram, right? So my constant here is -2. V has a value of -2 all throughout this first section here. And I know that that is going to then become the slope of my moment, right? So I start at 0, always start at 0. There's no applied moment or anything. And my V value becomes the slope value of my moment. So this line has a slope of -2, goes across 2 meters, so that's easy enough. -4, right? Just a simple, just linear, right? Because we had just a constant line. So next it goes to a first degree, right? Our polynomials, first degree, second degree, third degree is our linear, then parabolic, then cubic. So we're going from a constant to a linear function, first degree function. But then we're taking this second part here, is a linear function, is a first degree function, which means we're going to be moving to the second degree, a polynomial, a square function that has some kind of x squared term in it. So how are we going to go about that? How are we going to treat that in this scenario? Right, so we have this line, our V is negative, and it's getting more negative, right? It's increasing here. So that means our parabola, right, we know it's going to be a parabolic function, is going to be negative and getting even more negative. Right? And what is this value at the end here? Do I need my function to find that value? The answer is no, I actually don't, because I have this moment, my reaction moment from A is 11, and that 11 is pushing it back up to 0. So I know that this has to end at a -11 in order for my graph to get pushed back up to 0. Right, so it's not perfect. It's not, maybe the exact 100% immaculate placement of my parabola, but you can see the general shape of it. You can see where the maximums are. You can see where the greatest values are. How this moment changes from a linear to a parabolic. It's clear that it is going through a change from a straight to a curved line. Those are the things that are really important. You may want equations for the actual application if you're looking at specific points, but this is really a time-saving way of getting the general highlights, I would say, of your shear and moment diagram. Being able to pull the most important info, construct these in a quick way to see where you need info, where are maximum, where are zeros. All of these forms of information you can pull from these kind of quick and dirty, I would say, shear and moment diagram. Let's do another example. I now have a triangular shaped load, right? So a load that is not a 0 or not a constant, but that is actually changing, right? And we'll notice that our load is negative and is also increasing. So when I go to my shear and moment diagrams, what I want to do is take the info that I know first, right? So when I draw my shear diagram for this, pounds, one, it's going to be really easy to use those reactions at the bottom, the 240 and the 480, to go ahead and like give my end mark points. So this 241 shoots it up to 240 right here. And then that 480 I know is bringing it back up to 0. So it's going to be this 480 here. And then I'm just kind of connecting the dots between them because it's just one singular region of loading, right? There's no change. It's just one triangular loading region up to 120 pounds per foot. So the key here is your calculus knowledge, really, right? It's that knowing that this is negative and increasing and is a linear load function. If I'm integrating that, then I know that my slope is going to be negative, but increasing. So getting more negative, which we can kind of see if we kind of intuitively maybe know that because we have a linear function. We know it's going to be parabolic. So it starts out kind of negative and then dips down and gets more and more and more negative. Right, and we end up with a shear diagram that looks something like this. And it may not be exactly perfect. I may not have crossed in the exact right X location here where we're crossing 0, have a shear force of 0. But that's all right. We can solve for those things. We can go back to our equation and derive those equations for this and actually solve for what this X point is if we need to know that. But we have the general sense of the shape of the shear and moment diagram. Or I guess the shear diagram. We haven't done the moment one yet. So we could go ahead and pop in our moment one, pound-feet. And now we're going from this parabolic function, right? So something that is squared to something that is cubed. We're going to have a cubic function now. And what's that going to look like, right? Now we have this kind of split, these two regions that are going to cause a different looking moment diagram. So our shear now is positive, right? This side is all in the positive region, but is decreasing. So we're going to have a moment that has a slope that is positive, but decreasing, right? Kind of levels out more. Starts out with a steeper slope and then levels out. It's decreasing until we hit that maximum point where it crosses 0. Right? And then we see that our shear changes and now it's negative. It's negative and getting more and more negative. Negative and increasing. So it's kind of that slow negative and it drips on back down to this cubic. If we wanted to get these actual values, we would have to go back and use the equations. But we can get these general senses of shape. There were no applied moments here, so the moment graph was not affected at all by our loading guy up here, but instead was just based on this shear diagram. And now it would be very helpful, I would say, to have the crossing point and the maximum moment, but this gives us a really good starting place. Right, so maybe we only have to derive one equation and we're looking for one specific point instead of trying to derive a general equation. Take a look at another example. So this example that we have gets a little bit more complex, right? We have a fixed end, an end on a roller, there's a pin in the middle, it's got this internal hinge. There's an applied concentrated force, there's an applied concentrated moment, and a distributed load. So this thing has really got pretty much all you could ever want to load up in a problem like this, all in one. So what we're going to do is I've given the reaction forces already in our free body diagram at the top, and we're going to make our shear and moment diagrams of this. So our biggest thing is always kind of delineating those load regions, right? So where do we have those changes in load? Kind of give myself some dashed lines down. And they're really just to help me keep everything in line, keep everything a lot more visual to see where those changes in shear and moment are affecting each other, right? Where the change in load is affecting shear and moment. So I've got one at my 700 applied force and at that internal pin for now. And then we'll go ahead and just start breaking it down. Right? So our shear diagram, pop him in here. First thing we notice is we have this 1017 pounds that immediately pops it right up. So that'll pop it up to the 1017 and then no load until that 700 pound applied force. So straight across. Then we have that 700 pound applied force that immediately knocks it down 700. So we go down from 1017. Minus 700 gives us 317. So now we're hanging out at 317. Just go straight across. There's no other load. Put a 0, so we're staying constant until we hit that 150. That 150 pound per foot gives us slope for our next segment, right? It's just that slope of negative 150. Going down, and again, I don't have to guess where I'm ending. I know that I'm ending at negative 583 because this has to push it back up by 583 to get it to end at 0. So really, that's my whole shear diagram. Just walked right through every single load region to find my diagram here. Again, I would probably have to derive some of my equations to figure out where exactly this crosses, but it's good to know that I have a crossing point. For my moment diagram, now I can come and draw this guy in here. Now I have an applied moment in my end. Because of that fixed end, I immediately, on the left hand, have a 9,400 pound-foot applied moment. So that's counterclockwise, which means it's going to knock it downwards by 9,400. So boom, negative 9,400. Immediately starting out. This is the first example I think we've seen that has a moment that doesn't start at 0 because of that applied moment there. So we have that applied moment, and then by calculus rules, we know that our shear value becomes the slope value. So our shear value, or our moment, has a slope of positive 1017. Positive 1017 going up over this full distance. Right, so that brings me up to a value of, that goes over 8 feet. So 1017 times 8 is 8,000 something. So I do that 8,000 something minus the 9,400, and I get 1264 is the point where it hits right here, right where that 700 pound applied force acts. Now again, that 700 pound applied force does not affect the moment diagram, but it did affect our shear diagram. It changed our slope that our moment diagram is going to have. So we're going from a 1017 slope to now a 317 slope. A lot shorter of a slope, right? This is a more dramatic slope. And this guy, he's going to be a lot softer, right? 317 positive slope all the way up to 0. But now why is that 0? Why does this line go up to 0? How do I know that? Well, I know that because I know that at this point right here, there's this internal pin, internal hinge. And one of our rules was that if there's an internal pin or an internal hinge, the moment has to be 0 at that location. So I know that this graph takes it up to 0. I don't even have to do the calculation. Calculation will come out to 0 if I go ahead and do it, but I don't have to because I know that rule. And then finally, I go into this linear section here, where again I have this positive yet decreasing and then my negative. All right, so what I'm going to have is this linear function gets integrated, becomes a parabolic function with a maximum that occurs right where that thing crosses 0. Right where this crosses 0 is going to be a max on my parabola. And I drew this parabola a little bit wrong. Let me erase that. Because where does my parabola end? Right? Does it end at 0? It actually doesn't, because we have this applied moment on the end here, which is going to shoot it back up to 800. So this parabola actually comes up, hits its max, comes back down underneath, hits negative 800. And this pops it back up to our 0 value. So now I've got my shear and moment diagram for this beam that has this internal hinge.